Hello and welcome. Here we are in lecture 10. Uh, we've come a long way so far, right? We've learned quite a bit about Chisel, some things about Scala. Um, just recently, we covered more in depth about testing. And now we're going to go into the really, really fun stuff, talk about functional programming. So, functional programming, of course, is a rich topic on its own. And believe it or not, we've already been kind of doing a little bit in this course, right? A large part, there's many aspects that make up functional programming, but some of the key traits are things like, emphasis on immutability, having pure functions in the less hidden state. And we've been doing that, right? You notice how in our design so far, when we use Scala, we try to use val whenever possible to keep things immutable. We've done a lot of our constructions with recursive functions and that sort of stuff. In the Chisel world, and also in the context of this course, when I say functional programming, I'm actually going to refer to the operators we're going to see today. So things like map, etc., are ways for us to do operations on collectives, right? So exactly right. Very often in hard design, think about what they are. Building a single thing of something, easy. We'll write it up, no problem, right? But when a generation gets exciting is when we start doing things on multiple things. And with this functional programming concepts, we now have a much more graceful way to apply these operations. So in order to do that, we're going to talk about some of those things. We're going to talk about actually express anonymous functions in Scala first. And we'll cover things like map for each zip today. And then things like reduce and fold will be covered on Friday. And then there's some few details we'll leave, like flat map, for Monday. And of course, not only are we covering these in Scala, we're going to try and motivate them with some examples in Chisel. Okay, so we can go ahead and fire up a notebook. Good to go. Okay, so why are we even talking about this? Well, the whole point in Chisel is to take the best of software and make that power us to make more productive hardware, right? What does functional programming enable you to do? It enables you to do a lot of things, but in particular what we're excited about is to do functions over collections, right? So that means you have some group of hardware components that's in the collection, and you want to apply some operation to them. With functional programming, we can do this in very graceful and also safe ways, right? And what's nice is you can do a lot of stuff with for loops like you can today, but by using these functional programming operators, it can be much more concise and actually easier for us to check, right? So it's kind of this point of by using kind of a standard feature or pattern, it's less to write, but also it's easier for us to test, and also it's easier for people to read, right? We can say, oh yeah, I know what that is. Rather than trying to figure out what it is, we can quickly know what it is, right? You may also find by being forced to break your problem up into these standard operators, that reasoning and that, the result of your reasoning will help you perhaps better understand your problem and also help bring the compiler to help you identify when you get things wrong. And that kind of thing. And so the one, of course, caveat that says the functional programming in the beginning, it's all about, having everything exposed, no really hidden things if you can avoid it, mostly immutable. A lot of what we're going to try and do is we are going to have side effects, right? When you do Chisel, like you do an operation that connects two things, even though you didn't necessarily use a var, you can do it with vals, right? You're changing these internal objects that now have a connection, right? And so we are going to want side effects, but we want to do it in a way that is clearly expressed in the functional programming. And often we'll use FP for short in this course for that. Cool. Questions so far? Okay, let's keep going. So, what's interesting is this isn't just a Chisel or Scala thing, right? If you think about most of programming, you're working over collections, right? You may not think of it as a collection, but it's a collection. I forget the exact numbers. Like 80% of code is spent in 20% of the actual code because of loops repeating things. And so this is true in hardware as well, right? You often work in collections of things. Collections typically aggregate things that are similar. It's not a strictly a requirement, right? You can hook some collections of mixed types, but usually there's some sort of similarity to them. That's why you're grouping them together. And so we want someone to kind of operate on these, right? And so far we've been doing things like for loops or even recursive functions. The problem is every time we're doing that, like it's not like when we try and do some of these things before, every time we're doing this, we got to think about what we need to do. And then we type up for, we type up a recursive function, and we're kind of reinventing the wheel every single time, right? And it turns out there's some really common patterns. And if we recognize those patterns, we can just use some operator It provides that functionality. And then what's nice about that is that functionality, according to that pattern, can be checked by the compiler to make sure we meet those requirements of that pattern. It also is more for other people to come across that later on and say, oh, yeah, I understand what that is. I know that pattern. And I understand exactly what you're doing, right? So this is kind of cool. So in other words, rather than kind of having arbitrary for loops, what if instead we started using patterns over collections? And it turns out that only a handful of patterns actually covers a large fraction of the cases. And guess what? It may not cover every case. So what can you do? Well, you can compose multiple patterns to do more sophisticated things. And you'd be surprised what you can do. And even when you start composing these patterns, you can do an even larger space of things. Even that might not be enough. Yeah, finally, maybe to use for loops or recursive functions at the end. But you'd be surprised how much can be handled by this stuff. And so, yeah, this is kind of fun. If you've never seen this before, it's a new world. If not, you'll see how to use it in hardware. Yes. We will be doing currying. I wasn't trying to describe that right now, but that actually will be in today's lecture, believe it or not. Um, cool. So let's see some of those patterns, right? For example, the most famous one is map, right? So given some collection of input, you apply the function to each element of the input, and you get a new element of the output, right? So input element, apply the function to it, now it's an output element. And so, if you have n elements in your input, you now have n elements in the output. It's just the result of applying that function, so it's unary. And yeah, so that's pretty straightforward. What's interesting is inside Scala, when you call map on a collection, you're calling map on the collection. So it's a function implemented by the collection. It's not a built-in thing of the language. It's built into the collections that happen to be common in the language. And that's pretty nice. Actually, it's pretty graceful. So you'll see that a lot of the collections we work with in Scala are all from the main language or main library. The Scala collections library, I think, is a strength of the language. Even the developers behind the language will tell you that. And yeah, there's a zillion of these methods built into these collections, including things like map. So map takes an element, applies a function, has an output. There's also for each, which also applies a function to each element. However, for each does not have a return value. Technically, it's unit, which is like void. But so the reason why is, okay, well, why would you have both? Well, when you use for each, what that means you're conveying some sort of side effect you want to do, right? So technically, whatever you do with for each, you can do with map and just ignore the output. But here's an example of by using these patterns, we can clearly convey our intent, right? With map, we are really excited about the output. With for each, we're really excited about the side effects. And if you have code that wants both the output and the side effects, you're probably tempted to use map, but I would actually even argue it's better to break it into two calls, one for map to get the output you expect, and one for each for the side effects. We'll see some examples. Okay, so first let's look at functions. We'll come back to actually start using them. So this is a brief aside, but it's helpful. Scala lets you write anonymous functions, right? In other words, you can write a function that's not properly named. So we've been doing def functions since the beginning. But yeah, what if I just said, hey, what about a function that given an int x just adds 1 to it, right? That's how you write that. So this is they call a function literal, but you might call a function an anonymous function in our languages. This describes a function, right? It takes an input, does something to it. What's fun about this is, of course, even though right now here it's anonymous, it's literal from the interpreter, we can, of course, assign it a name. So we can assign it to a val. So now this val inc holds this function literal. Of course, we can define the function normally in exactly the same way. Oh yeah, sure, we define the function. We can apply something to that val, and it does the right thing. We can also apply it to the function we defined before. We can define function literals on multiple inputs. Sure, no problem. But I guess the key thing to kind of grab from this is just in Scala, the syntax is arguments, arrow, function body, and these are all, trivial one-liners, so there's no need for parentheses. Yeah, you can, put these with braces and make it longer. That's totally fine. But yeah, if you start finding yourself writing multi-line functions, I recommend in those cases just doing a traditional def and not worrying about it. These one-liners are nice for functional programming operations where we're doing really simple things. We said if you have a complicated operation, put it inside a def and do multiple lines. Cool. Still all on board. Okay. Let's try with map now. So with map, map's available on a collection. Let's say like a seek, right? So we have a seek, in this case, L, which is just, 0 through 5, right? So maybe we'll go ahead and even just appreciate L first, right? Okay, yeah, 0, 1, 2, 3, 4. Sure, got it. Um, so I can, map a function that's given an element and produces an output. Sure, no problem. If, for example, let's say I took in two arguments, it's going to complain because, wait a second, map takes a single element, and here I'm trying to give it two arguments, so it's not going to be happy, right? You have that matching up. Okay, sure. So here I use a def originally. Remember I said before in Scala, you can, remove this dot and parens, and you can make it look more native. So I actually love this kind of way of expressing when you have like a map and it's like really clear collection space, map space, the function you're doing. To me, that's a really clear, nice syntax. Interestingly, the style guides and the time of writing Scala have changed, where they're now recommending folks be more verbose, more explicit like this. And it's not just because sometimes people get confused what happens here. It's actually because they're anticipating more non-Scala developers and they're trying to be more like other languages. And so for that reason, they're encouraging this, but I'm stubbornly trying to do it this way when I still can. So I think it's really pretty. Okay, so here we have the function previously defined, right? We, of course, can use a function, literal or anonymous function, right here. So we can say, hey, let's just give an I apply inc. Or if we, without even defining inc, we could just say straight up, yeah, just give an I, add one to it. So this is pretty cool, right? Imagine trying to do this without the functional program, right? You'd probably be like, oh, shoot, okay, I guess I got to do something like, uh, number one, you probably need to use mutation, right? But okay, I need to like create a new thing and then append an element at a time by modifying it or something. And you can see now how it's possible operations like this where you really don't need mutation that much, right? We can give it a collection, I want to make a new collection that maps each element one to one something else. Boom, you can do it off map. Yes. So it makes a new seek. Yeah. So after writing these code, I've just taken advantage of this being a garbage collected language. We put a lot of stuff in the memory of the system, right? We have originally there's L, which is some place in memory, and because it's pointed to by this reference L, it has to hang on to that, right? It can't ignore that. These other ones could be garbage collected, right? Because nothing's referring to them, so there's no way to get back to them. But yeah, these are all potentially going to be different pieces of memory. But like I said, this is part of the beauty or the Cosmos kind of approach is that we're not thinking about memory allocation, right? We're letting that be handled by system, and we're trusting the garbage collect. So it's going to worry about memory management. That's their problem. And the good news is for hardware designs, even when you have a really freaking big hardware design, the memory required for it isn't as huge as you might expect because of this kind of stuff. Cool. Okay, so map. Now, as you see on the slide, right, applies a function one by one to each element. You can't assume it's just they're going to go, increasing order, right? In theory, you should think about it like the diagram. Uh, only take this as input, and then you'll know the order is being applied. Now, technically, you can be really sneaky, right? And if I did something like I plus 1 plus L0 is probably going to work, and you shouldn't do this. Well, 0, that's going to be 0. Let's do like L3, which is not 0. Yeah, that does work, right? But if you think about that, it's a little bit weird, right? It's not totally weird, but it's a little bit weird, right? Because the whole point of trying to function takes one thing in at a time. And here now we're kind of peeking someplace else, right? Oops, what if I like did something else? Like, what if I said like, oh, I want, I plus, 3, and then I took all of that. Oops. Uh, I plus 3, and then I took that mod the size of L to make sure it doesn't overflow. Yeah, so you can do all sorts of weird stuff, right? Um, but just because you can do it doesn't mean you necessarily should. So Scala gives you a lot of freedom in some ways, but to keep map being that pattern, so part of the point of using these operations is to be a pattern folks can recognize, right? Map being a pure thing, takes one element for the input, one element for the output. It shouldn't depend on multiple things. Now, maybe you want to include all information inside that function, and that's where the currings can come in a few minutes. Yeah. Correct. Yeah. So map should be stateless, right? It's just applying this function to every element, and we should make no assumption about the order in which it's applied. So I think of it as parallel, but it could be any arbitrary order it's applied. If you start caring about the order which is applied or communication between elements, that's Friday's lecture. So like the map, they should be independent. They should be independent things that are completely parallel. If you want to have communication between elements, it's a different pattern and reduce and folder ways to get that idea across. Okay, and then for each, like I said, for each still applies a function to every element. Just the difference is there's no return value. And so although you can technically do this with map, by using for each, we can convey to people that there's no intended return value. And it's key to someone else reading this code, like, oh, wait, this function has a side effect. That's the reason why they're doing it. And like I said, it's good to avoid if you can, but not always to have side effects in maps, because otherwise people get confused, right? So if the goal is a side effect, use for each. If the goal is the output, use map. Sometimes you need to do both, and you can kind of decide and chisel what's the smoothest way to do that. I often sometimes encourage people to do a map and a for each, like to break the thing you want to do. It's called loop fission, breaking it apart. You can do that. Or you can do it in a map and just be really clear about documenting and realize you've made your code harder to read. Sure. So for example, a lot of times in Chisel, what we're trying to do is we're actually trying to have the side effects like connecting things. We're going to use for each. Cool. So let's try them both inside Chisel. All right. So here we have this, simple module, which is really simple. We'll do some more sophisticated ones in a few minutes. And our goal is just to produce a vector, which will simply be the constant scaled out, right? So in other words, given some number of elements, we're going to simply just, have them all be that value, right? So we're going to show both map and for each here and kind of how it fits together, right? So, okay, so let's talk our way through this. So we declare a bundle if, vec number of outputs. Sure, we've seen that before. We have, a bunch of uints. Sure, we'll do a range. We've seen those. Now, right now, these are Scala ints. We can turn these into chisel uints with a map, right? So the whole point is the output, right? So now we're taking as input Scala ints and mapping these to chisel uints, right? So now we have a sequence of chisel uints, right? Did the .u on all of them. And then we're going to go ahead and, so this thing's not anywhere in the output, by the way. It's just us showing off you can do this. But then the actual output is going to be a constant, right? And what we do for the actual output, we're simply going to take every output and connect it to the constant as a uint. So in this trivial example, we're using a for each, right? Because there's nothing returned, but the thing that matters is the side effect. The thing that's the side effect, this connection we're making between each output in io.out and this constant. So you can imagine this code when it gets emitted. Yeah, you see we keep doing this. We can take advantage of being parameterized. Sure, we can have 4 things connected to it. This is a trivial example, but it gets the point across. So yeah, for example, connecting a lot of outputs, perhaps you can use something like for each sometimes. This portion extends not in the Verilog. So if you're looking for this in the Verilog, you're not going to find it. It's just showing how you can apply map, right? Here to a point was the transformation. So guess what? Now we have a seq of chisel uints, right? Which, based on what I taught you so far, you wouldn't know how to do. Maybe you could use tabulate, but otherwise we kind of a pain in the butt. Yeah. Correct. They're dead code and they're not going to be emitted. Yeah, they're there to show map, but they aren't going to be emitted. Yeah, I can even make that extra explicit. Okay, cool. So now we have map and for each. Oops, let's go ahead and keep going. Okay, so we kind of keep interspersing a little bit of Scala. And the reason why we're kind of interspersing a little bit of Scala in this lecture is because we need to know just enough of this functionality in order to do what we're trying to do, right? And so one thing that comes up is sometimes you want what's called a tuple, right? So this is common in programming where you have things you want to put together. And so you can think of it almost as like a struct where you don't name the fields, right? Another way to think of this, right? It's a collection of things. They're often heterogeneous. Otherwise, it would be some sort of array or collection. So Scala provides these. And so you see, for example, down here, we have a tuple T1, which in this case, they're homogeneous, right? They're both ints. But this one's heterogeneous, right? And you can access the elements of them by doing the syntax of dot, underscore, and then number. And for heaven knows what reason, they start from one. Um, so you see right here, for example, we have 2 comma 3. So that's going to be um, right here, these 2 3s, right? What's interesting is you can also use them a lot of places. So we're going to use them as a way to concisely express arguments in our function literals in a second. That's why we're covering these. We're going to use them to, like I said, to use arguments in our function literals. But they're handy, right? In this case, for example, T1 is a tuple. We can now use it as a way to assign 2 different vowels at the same time, right? That's totally okay. If I try to do 0, it's going to yell at me because that's not a thing. Like I said, it starts from 1. That's to me an oddity. I think Marno Dursky, one of the videos I watched, tried to justify that, and I've long since forgotten what its rationale was. But okay, going back to why do we even have these, or what are we using them for? They're best when you have a situation where you have whoever's producing these tuples and whoever's consuming these tuples really near each other. Because yeah, you can see if there's a couple of things, like a pair of things, sure, this works fine. Once they're having like 3, 4, 5 things in the tuple, and you have like function in one class making it and function in another class consuming it, just use a case class, label things, right? It'll be much more clear, right? It's better using things like a case class to be really clear what's what and that kind of stuff. But sometimes when a producer and the consumer are really close to each other in your code, there's a couple of things you want to kind of pass around at a time. That's why we'll need tuples. In a second, we're going to see zip. That's one of the reasons we're going to use tuples. In a few lectures, this we call pattern matching with case. Also can use tuples. But yeah, like I said, use it sparingly. If it gets too complicated, just use a case class or even a proper class. Cool. Questions? Okay. So then, as promised, what about zip? So actually, I found it's easiest for zip to go forward a slide and show you the diagram, right? So zip is given 2 collections. Technically, you call zip on one, the other one is the argument, but really you're given 2 collections. It goes through and pairs up the elements, one by one. So takes element from collection 1, element from collection 2, paired up. Now we have a tuple that's a pair of these 2 things, right? One by one, one by one. So naturally, the question you might have is, well, what happens if these collections are different lengths? It's going to pair them up until the shortest one runs out. Usually, however, you should probably make them the same length. If they're not the same length, that's probably a bug, but not always. But what does Scala do? It goes until it runs out. And so whatever one's the shorter one is what you're going to get. But yeah, so you have 2 collections and you want to work on both elements at the same time. This is the way to do it. Okay, let's go back and actually see it, right? So pairs of collections from one thing. So technically see you have, the original thing and then the argument technically, but really it's 2 collections. Both map and zip, for example, are in Python. So you probably maybe have already seen these. You played around with them a little bit. Remember in Python, you also have like lambdas, which are kind of like anonymous function littles we were just talking about. So there's some of that functional programming stuff kind of snuck into Python as well. So why do we do this? We often combine things before doing operations. So let's have our range. We can zip it together. Oh yeah, so 0, 1, 2, 3, 4 now zipped is 0, 0, 1, 1, 1. It's the same thing over again. If we give it a much shorter sequence, like I said, it only does as long as the shortest sequence is. Okay, and then now I can zip the 2 of them together, and here's why we covered the things we just covered. We covered both tuples and the stuff. So now we have a case of these things being combined, right? So we have these 2 arguments coming in, and yeah, we're gonna go ahead and add those up. Just like that. And so the use of the keyword case here is maybe perhaps a little surprising. That's kind of us telling the Scala compiler, oh yeah, by the way, there's going to be a tuple. I want you to match it up. If you remove it, it's probably going to give an error. Not always. Yeah. And it's consider adding pattern matching. And then that's why I want you to put case in there. But yeah, basically now we've taken this tuple coming in as input, and we've now labeled both of those tuple inputs like we just did in the prior slide. Remember, I kind of showed you at the very end. Oh yeah, you can label a tuple as 2 variables or however many variables it is. That's what we're doing here. And helps us kind of get the thing we want. In this case, we're adding up the pair of things on each element. So we zip them together first, and then this result, which, was like this, we then add up the pairs internally to get to other things. So there's a function that takes in a tuple and produces a single int. And so you see, oh my gosh, we just kind of did a compound operation, right? We did a zip followed by map. So like really concise, really simple, but also pretty graceful, right? You can imagine like some sort of super fancy compiler. If it wanted to, it should be able to parallelize the hell out of this, right? Because we know the semantics of zip and map are such, things are quite independent. Because of the immutability and lack of side effects, things should really be independent. Should be able to do all this kind of stuff. Now, I don't believe it normally does that in parallel, but there are parallel collections in Scala where it can do things in parallel. Yes. Okay, fantastic question. Why doesn't a syntax highlight the zip and map? Those are like keywords right here. Shouldn't those matter? Um, they definitely matter. I don't think it's intentional. I suspect if we're writing this in IntelliJ, for proper Scala syntax highlighter, it probably would highlight them. But I have no idea what combination of syntax highlighting we're getting here with the combination of Jupyter plus, Almond running and stuff. If I turn it into a function call, it probably might change. Let's see. No, it doesn't change. But yeah, no, zip's a keyword. It's important, but it's not being highlighted. You're right. Cool. Other questions? Okay. So that was zip. Have these diagrams kind of showing it. Let's try and put zip to work. Okay, so this is another example. We're going to put some things out there. This one, is another simple made up function. Given a input vector, we're going to apply the absolute value function to all of the elements in the vector, right? So, absolute value given a sint. If it's less than 0, we're going to negate it. Otherwise, leave it alone. And so, what are we going to do? Well, at our core is this for each, right? We want to basically say, hey, for every output connected to the corresponding input with the absolute value applied. But notice, what are we applying on? We're applying it on this tuple, and this tuple comes from a zip call. So basically, we're taking all of the outputs, zipping them with all the inputs. So now, input 0 is zipped with input 1. Or sorry, input 1, or no. Input 0 is zipped with output 0 in a pair. Input 1 is zipped with output 1 in the pair, right? And so we have this pair now after the zip call of all the inputs paired with each of their corresponding outputs. So I'm using the notation of, output, input. In this case, is the kind of convention I'm using. And yeah, we can go ahead and connect them. And instead, because the important of this is the side effect, it's not returning anything, I'm using for each. This will work perfectly fine with map, but I think for each is more clear. And just look at the code right now. It's proofs of Verilog. Sure, you can see that the actual absolute value is being done. Where here's the negation, and then whether or not does the negation is being controlled by ternaries and mux. But yeah, if I do a map, it's gonna work perfectly fine. But yeah, I think for each is kind of more correct and more clear what's going on. And you kind of wonder, okay, well, let's say I didn't do it with the functional program operators. How might I do this? Well, you might do it with a for loop, right? For number of elements, connect each output to the corresponding input, the absolute thing applied. And guess what? Produces exactly the same Verilog, right? It's exactly the same fertile graph and produce exactly the same Verilog. It's just, I said, to get more familiar with functional program operators, you'll find that this is kind of a much more clean, elegant way to do it. And like I said, when you're reading a for loop, you got to think to yourself, okay, wait, what are they iterating on? What's going on? Because for loops are very, very general. In the case of this is not general, right? It's actually a really simple pattern. Simple pattern of one and one for each of these two collections. Well, hey, let's zip them together and then for each iterate on them. One thing worth noting, which I kind of glossed over, is that these aren't even seeks anymore. These are now chisel vec. So chisel vec implements map, implements for each, implements all these various things, and that's available to us. Yes. Um, you're saying if I called zip on io.in, so like if I took this code, instead of doing it that way, I wrote it like this. So this is going to break initially because this is now backwards. But if I simply flip this, it's also going to work. But if I didn't have that flipped, it's probably going to break. Let's see what happens. Yeah, well, in this case, it's warning me, wait a second, I can't connect an output to an input. That's telling me that's not correct, right? But if I do it the other way around, totally fine, right? Input to output, yeah, totally fine. Um, you're right. It was kind of an arbitrary choice I made here to put out on the left and make O first here. These two need to be consistent, but whether it's output comma input or input comma output, you can imagine either way. I guess to me it was more clear because it was output, input was the order over here. But no, you see, the other one works just fine. Yes. Oh, can a compiler detect if things are side effect free? Good question. So there's a notion of can a compiler detect if things are side effect free, and is a compiler required to make it side effect free, right? So Scala is pretty permissive, right? You can have map operations that mutate tons of state, right? It's not a pure functional language in that sense, right? It's not really enforcing that on you. Um, but yes, smart compilers can do code analysis. They can do escape analysis, and they can see, okay, was this possibly touch? Believe it or not, similar analysis is done even in C compilers, right? So when people think about, oh, it's really important for me to put, const keywords in my C code so compiler can optimize the heck out of it. Um, it can read a simple function body and tell what you're touching, right? Unless you're doing pointers, it can tell very unambiguously what you're touching. And so the const keywords are mostly for you to not change something you don't want to change or to convey to humans this should be constant. But from a point of view of an optimizing compiler for like C, for a few decades now, if you have a simple function and it's not using pointers and it's just working directly on like scalar variables, yeah, it can tell exactly what you're touching, what you're not touching, and knows what you're modifying and not modifying. And so Scala compiler has some intelligence to it. However, don't see compiler as the enemy. Work with it, right? If you aren't trying to do a bunch of side effects, use patterns that both humans and compilers recognize as, conveying there's no side effects. In this case, the whole point is the side effect. That's why we're using for each, right? And as I said, the side effect is that, as a result of this connection operation, both the output port and the input port are now changed, right? Because now that connection being made. So that's the side effect. Cool. Great question. Other questions? Okay. Let's keep going. So I'm kind of keep sprinkling in more and more Scala syntax throughout today's lecture. Um, this is one thing you may have seen me do before and I didn't really explain. Now I'm going to explain. It's called a function placeholder in Scala, or I call it like a wildcard. Basically, rather than having this syntax like down here, if I want to like say add one, I have to say, oh, I'll give it an input, add one to the input. You can just say add one. Very concise, same operation, same functionality. But you can imagine it's one of those things which is really powerful when used judiciously, but if you use it too much, it can be really hard, right? So what's exactly the semantics of what we're doing? This underscore is what they call a placeholder. If you like a wildcard, it's going to take the arguments in order. So right now, if I have like a single unary function, which you need for map needs to be a unary function, a single input. Sure, that single input, whatever operation you want to apply to it, you can do it just very concisely. Now, let's say I want to use this thing in two places. Let's say I want to like maybe double it. Rather than doing times two, I want to write like this. It's going to break because it runs out of things. Every time you use this placeholder underscore, it moves on to the next argument. So if you have two underscores, that means the function you're calling this for needs to take two arguments. So we'll see that actually in Friday's lecture when we do reduce, which is to take binary functions, take two arguments. Sure, we'll be using the two underscores. But for map or for each, which takes unary functions, you only get to use one underscore. If you use more than one underscore, you can't use placeholders. Just do a regular function like this. So it makes your code simple and clean and short. Good. If not, explicitly name your arguments. Cool. Still on board? Yes? Okay, let's keep going. So remember when we did an arbiter just last week, right? We did a few different versions of it, but our final version, we said, okay, well, given the number of input ports in the back, remember these are all decoupled. We have our output, whoever, gets passed on to the next level. And remember, these decoupled ports are bidirectional, right? And so the ready signal in these ports convey back to the person on the other end that they won the grant from the arbiter. So remember before, okay, we want to build up this collection of valids, collections of bits, then use a priority encoder with the valids. And then we had this for loop we went through and did a lot of connections, right? Kind of set up all the ready signals going backwards. We had to aggregate all the valids. We also had to aggregate all the bits. We also need to do an OR reduction and also connect the bits. So there's a lot of stuff going on. And remember, this was our most concise version from last time, right? There was earlier versions of this code was more verbose and longer and more complicated. So this works. We know we covered this previously. But now we can take the same code and we can make this a little bit tidier with functional programming. I'm going to go back and forth to kind of highlight some of the key things. First off is let's try and get that wire full of valids, right? So before we said, okay, I want a wire of all these valids. So first I declared this vec, and then I went through and connected them, one by one with this for loop. Instead, we can just do this like this, right? Hey, for every one of those request ports, just give me the valid port. Using that placeholder syntax, using a map, because in this case, we really do care about the result, right? So boom, that was effectively like 3 lines, right? We had the declaration of the wire, the for loop, and then the thing. Now that is 1 line, right? We just grabbed all the valids. Really easy. You can just grab them all together. Now, from before, remember we had that OR reduction to produce the output valid. That's unchanged, right? It's a little bit different syntactically because, here we had an OR reduction. The OR reduction operator in Chisel is only available on uints. Here we did a little bit of casting business where we, made a vec out of this. And then with that vec, we then casted uint to do OR reduction, which is essentially the same thing. Like before, we did our chosen one hot. Okay, from the priority encoder. Remember when it came to the bits, we actually made this wire as a vec, connected all the bits together, and then we assigned it like this. We actually can now, like we did for the valids, just gather all the bits, but like that. So that's all the bits. We didn't even bother naming it. We just pass it as an argument to the mux one hot. So extremely concise. You see functional programming is extremely concise to do kind of, not just a single operation, but operations over entire collections. Extremely powerful. That's pretty spiffy. And then at the very end, we had this portion, right? Where we're connecting a port from the input, from the IO request coming in. And we also want to take something out of this vec of the chosen one hot and kind of put these all together. And yeah, we can do that. We're going to use a zip to combine those two things. And then for each of those, simply just do that connection again. Perhaps there's better of a space there. So that's pretty cool, right? So the functional programming, you can see, look at our code now, right? No loops, no vars, expressing the full parallelism that is there, pretty concise. Now, I would argue this one, I would think is a pretty good use of this. You'll see later on that you can get a little carried away and things get way out of control. But so far, so good. Questions, comments? Yes. Oh, great question. Okay, how to reconcile the notion of functional programming, which is supposed to be stateless, with the fact that in hardware design, we make components that have registers, which it counts as state. Great question. Let's keep the two things separate in our minds, right? There's a difference between the hardware we're producing and the Scala program we're making that produces that hardware, right? So the functional programming is in the Scala program that produces that hardware. And yeah, to our best effort, we like to have that be functional, etc. But you see me, right? I'm not a total purist, right? Occasionally I'll use a bar like before. We'll have some stuff here and there. But that can be mostly functional. But remember that the actual chisel hardware, which has registers in it or something, that's the output, right? And so, as I keep saying, right, the whole point of our chisel programs, they're Scala programs that happen to just instantiate hardware components and connect them together. That's the goal. The fact that some of those hardware components are registers versus not registers, it doesn't really matter from the point of view of the Scala portion, right? Because remember, in Chisel, right, we don't have some sort of weird inference about, I want you to infer a register here. No, we say quite explicitly, this is a reg, right? We explicitly instantiate them, and it's just another node inside of our third graph, another node inside that graph inside the program. And so, yeah, they get directed like I said, construct things, connect them, right? And so the Scala functional programming can do all that, right? In this case right here, we have all of our IOs, and most of what's going on inside of here is actually really just connecting the IOs, right? At this point, technically nothing's been made. We've actually just made a seek of references to certain fields, right? We actually haven't even made anything. This is actually not creating any hardware, this line right here. Um, this does, right? This does an OR reduction. Don't worry about the cath for chisel, but the important thing is this is an OR reduction. Yeah, that will create a bunch of OR gates to do the OR reduction. That's actually making hardware. This is making hardware, right? This is making a priority encoder. We're connecting all of those references to this priority encoder. And so that's why we do, once we hassle having invalids, now we have all those things available to us. This actually makes hardware. This, of course, instantiates a mux1 hot. That's also hardware, right? Connecting the output of that prior block, right? As well as the other input, we didn't even bother grabbing in advance, right? We just did it in inline, right here, embedded. That's totally fine. This is getting a collection of references to the certain field within those bundles, and this happens a lot where you have things coming in, and bundle groups together different things on the same port, and sometimes what matters more is getting the same thing across all ports than any individual port, right? And so this is what we're doing right here. And also, once again, this final line, what are we making hardware-wise? We're not making any hardware, we're connecting hardware, right? There's already this input ports ready signal, as well as, this stuff here. And so we're going to go ahead and take the output from the chosen one hot, which comes from a priority encoder, and that with other input port. And then that's been connected to the input port. So here I'm using, I for, input and C for chosen one hot. Perhaps you prefer more verbose names. That's totally up to you. But like I said, once again, this is extremely concise, right? And this is what happens in functional programming, is you often get these really powerful, very concise things. As you saw on like the prior slide, or a couple slides ago, where I even did like multiple operations in the same line. I did a zip and a for each in the same line. You can do multiple operations in a line. I find that 2, maybe 3 is about the limit. You can write way more. And when you write it, you're like, oh, that's awesome. You feel so proud of yourself. And then 3 months later, you read that code, you're trying to debug it. Or worse yet, you're reading your colleagues wrote that code 3 months ago, and you spend time parsing it. It's not helpful, right? So value readability. So today, I deliberately did not go too far, but in some of the next few lectures, I'm deliberately going to go too far to functional programming, so to speak, and we'll kind of talk about how to bring it back and scale it back. Cool. Other questions? Okay, no reason to force it. This is way short. This lecture is usually not short, but I guess there was less questions today. Cool. Sounds good. That's all, folks.